Good afternoon. So what's going on? Let's see. I see everybody in Hopi except Jada. Is she coming?
Yeah.
Okay. Well, you guys can stay. I don't mean to kick you out. Let's see. And Tobias in Mogian told me he's got a baseball game.
Right. Which
Hey.
we talked about that earlier, but
Okay.
Courtney's here.
I mean, I can come do Calc 2 today. I'm just kidding.
Please do. Please do. I'm hurting for students today, so.
I'm not that good yet. I gotta brush up on my math skills.
That's okay. I'll take you as you are. Come as you are.
That's why we like you.
Anyway, so how's softball going?
I actually quit the other week.
What?
Yeah.
I thought you were like superstar and everything.
Oh, yeah.
No?
Superstar bench player.
Oh, okay. All right. Well, you got to do
It's
what
okay.
you got to do. So.
Yeah, I was falling behind on school, so
Well,
school takes preference.
apparently that doesn't concern my students. Sorry.
Yes.
That was kind of a rude statement, wasn't it? I didn't mean that, did I, Miss Townsend?
No. I had some good conversations today, though.
Oh, good.
To let you know without saying names or anything.
Right, right.
Because I couldn't decide what to do, and so, yeah, it's all taken care of.
All right, well, good. Well, I hope you whip him into shape. That's what we need.
I'm hoping you start seeing some things happen, is what I'm hoping.
Okay. All right. Well, let Mr. Tomlinson in this class know that if he needs stuff reopened since the midterm, we can work on that. Okay.
I will let him know that.
Now, if it's before the midterm, then I don't open stuff up before the midterm, but.
Okay. So
anyway.
I don't see any problem with that.
Okay. All right.
That's giving a lot. I mean.
Yeah.
I think you do great, so we appreciate you.
All right. Well, thank you.
Thank
Bye,
you.
Mr. Sean.
Bye. See ya, Courtney.
You got students. I'm gonna let you go.
Oh, Miss Jeannie.
Yeah.
I did send the rest of the guided notes for calculus for the rest of this coming chapter. So
I did.
Just kinda be
I
on
did
the
get an email from you. I haven't had a chance to look at it, but
okay,
I did.
well, that's what it is. It's
Okay.
most of them are just one page, but there's a lot of them. So
Okay.
All right. Thanks.
I will take care of it. We'll see you
All right.
later.
We'll see you. All right. There's Jada. All right. We've got Weston here. Good to see you guys. All right. So today we are going to be working on 10.3 and quite possibly 10.4. So do you guys have any questions before we get started? All right. So Weston, you said you were kind of working on catching up. I looked at the videos to see if yesterday's. I mean, I guess you were here yesterday, but anyway, this week's stuff still hasn't posted to the video. So anyway, but at least we got last week's for the most part. So anyway, so keep working. Keep letting me know. Jada, if you need anything reopened, let me know from chapter 9 or whatever. But chapter 10 is going to fly by because all these sections from the rest of the way are super short. And so we'll do at least one section a day. We might even do 1.5 to 2 sections some days. Okay, so just to let you know. So you really need to keep up. Okay. All right. So let's start with 10.3. All right, so 10.3 is on what's called the integral test. Okay, and so this is a test for convergence, for series convergence. So we'll kind of work to that. So, but it doesn't start off with the integral test. It actually starts off with kind of a continuation of when we talked about a series being bounded. Okay, so the first theorem here, it says a series of non-negative terms converges if and only if its partial sums are bounded from above. Okay, so that kind of makes sense, that if the series is so bounded from above means that there's a cutoff, it doesn't go to infinity. So if it goes toward a sum, then it converges. Now, this also means it does not converge if the partial sums are not bounded. Okay? All right? Okay. All right. Let's see. What else? So let's say if we want to know does this series converge or diverge? Okay. Now, this is actually the series of 1 over n as n goes from 1 to infinity. This series actually has a name. Okay, there's not very many of them that have a name, but this is called the harmonic series, 1 over n. Okay, so this one's gonna be important that you know the result. All right, so this is kind of how we think about this. So when we plug in 1, we get 1 over 1, which is 1. Then 1 over 2, then 1 over 3, 1 over 4, 1 over 5, and so on. Okay, now. So here we have 1 plus a half. Well, the sum of the next two numbers is greater than or equal to a half. And then we can group the next two and we get a sum that's greater than or equal to a half. And so if you remember where we did the cluster idea before, if we can take clusters and continue to get numbers that are bigger and bigger and bigger, okay, this is going to go on forever. Okay, so that means that there is no upper bound. So if there's no upper bound, then this series diverges. Now you might say, well, wait a minute, couldn't we have done this by the nth term test for divergence? Well, if you remember the nth term test for divergence, the limit as n approaches infinity of 1 over n is 0 because you get 1 over infinity. So if you get 0, it's no help. So the nth term test gets us nothing. It's the fact that there's no upper bound to this series that lets us know that it diverges. Okay? So what you actually want to really get out of this example is, number one, if there's no upper bound, the series diverges. And number two, the harmonic series, 1 over n, diverges. That one you want to memorize. The harmonic series, 1 over n, diverges. Okay? It's going to come up so much. All right, so then if we look at the practice problem, so here we have the sum as n goes from 1 to infinity of 2 over n. So what do you think? Would that converge or diverge?
Would it diverge?
Okay, so explain your reason. You're correct. Explain your logic.
So I kind of thought about pulling the 2 out, like putting it in front of, and so
Yes.
then it was just the harmonic, which diverges, and so 2 even if the two converges. It's like a rule, I think, from the last
Yes.
chapter. And so it
Yes.
always diverges.
So if you have a positive constant and you're multiplying it by infinity, it's just going to get bigger. So yes.
Yeah.
So this will diverge. Okay. So Jada, did you kind of follow that logic there that he was talking about?
Yeah.
Okay. So any positive constant times a diverging series is also going to diverge. Okay. Good job. Good job. All right. Next is now we're going to talk about the integral test. Okay. Now the integral test is kind of different, kind of interesting, because what you do is instead of testing the sequence, you test the integral. Okay. And now, so it says that if suppose your a sub n's is a sequence of positive terms, and the a sub n can be written as a function, where f is a continuous positive decreasing function for all x. All right, then the series and the integral either both converge or both diverge. So what you can do is test the integral, and if the integral converges to a number, like if you get a number, then it will converge. But if you get infinity or negative infinity, it will diverge. Okay? So I do have some students that are really good with integrals, and so they practice this integral test. The interesting thing is that a lot of the problems that we do in the rest of the chapter, we can do by the integral test. The problem is it's not always the easiest way to do it. Okay? So I kind of think of the integral test as the closest thing to the adjustable wrench, because it actually does more problems than any of the other tests, but it's not always the easiest one. So, but as we go, I'm hoping that you'll be practicing these, that the practice problems for each of these only take like 20 minutes, but you want to practice and get good with each of these tests. Okay? So let's get good with the integral test. So here we go. So let's say we want to know, does this converge or diverge? So see, just looking at the numbers here, see we've got 1. When we plug in 1, we get 1 over 1, and then 1 over 4, 1/9, 1/16. So these are going to 0. So the nth term test doesn't help us. Anyway, it's kind of hard to say. So here, if we use the integral test, then what we're going to do is the integral from 1 to infinity of 1 over n squared dn. All right, now. Okay. So one thing that you just kind of have to remind yourself of is that when one of your limits of integration is infinity, that's an improper integral. So we have to rewrite it. Excuse me. So to rewrite it as a proper integral, we're going to write this as the limit as b approaches infinity, and then replace the infinity with a b. So now this is a proper integral. Now, as I rewrote it, just to make it easier to do the integration, I rewrote 1 over n squared as n to the minus 2. And now to do the integral of n to the minus 2, I add 1 to the power and then divide by that new power. So that's going to give me negative 1 over n. So this will be negative 1 over n. Same thing. Okay? So now I plug in the limits of integration. So I get negative 1 over b minus negative 1 over 1. So now I plug in infinity here for b. So any constant over infinity is going to go to what?
0.
0. So I'm going to get 0 minus -1. So that's 0 plus 1. So it's 1. All right? So when I do that limit, when I do the integral, if I get a number, then the answer to the original problem is the series converges. So if I get any number. Now, here's the thing though, is that the series doesn't necessarily converge to 1 because the integral is actually could be bigger than the series. So we know the series converges, we just don't know that it converges to 1 necessarily. So in these problems, most of the problems I'll ask you, does it converge or diverge? So in this case, we don't really know what it converges to. Well, we know it converges to 1 or less. Okay? All right. So now let's look at the practice problem. Oops. Okay, so just before the practice problem. So what this is saying is that the series is always less than or equal to the integral. So if the integral converges, we know the series converges. But we might not know exactly the number. Okay? All right. So, whoops. So, you know what? Okay, so on practice 2, if we put a 5 in front of that integral, okay? So if I put a 5 in front of, of the summation sign. So if I have a 5 in front, then will the series converge or diverge? Jada, what do you think?
Converge
Okay, explain your logic. You're right.
because the 5 doesn't make a difference
Right.
because of the rule.
Yeah, because we just did 1 over n squared. We said that converged. So multiplying it by a constant doesn't change that. Okay? So what's happening here is I'm trying to teach you some of the basic ones that converge and diverge. And then multiplying by a constant doesn't affect it. So if you know kind of the basic ones. Okay? So this converges. All right? Okay, so now we're going to kind of compare the last 2 types of problems that we had. All right? And what they are is they're called a p-series because they're of the form summation, a series as n goes from 1 to infinity of 1 over n to some power. Okay, that's the p-series. Now, when p was 1, we got 1 over n, and that was the harmonic series, and that diverged. But when p was 2, we did by the integral test, we found that this one converges. So, what's the rule here? All right? Well, the rule is that it converges if the exponent is greater than 1 and diverges if p is less than or equal to 1. Okay? So this is what you need to write on the line, and that's what you need to learn. Okay? So when it's a p series, 1 over n to the p, then you look at the exponent and you say, okay, if p is greater than 1, it converges. All right, so to apply that rule, see, all you do then is, if you want to know, does this converge or diverge, then you recognize this is a p series. Okay, 1 over n to the p. In this case, p is 3. And so you don't have to go through this integral test. If you see that it's a p series, see, I mean, yeah, we could go through the integral test, but if you just happen to say, this is a p series, p is 3, that's bigger than 1, so it does what? If p is 3?
Converges.
It converges. Okay? So that's kind of an easy one. All right, so now let's look at practice 3. So does that series converge or diverge?
It diverges
And why?
because it's less than 1.
Yes, because the p is less than 1. 1/3 is less than 1. So if p is less than 1, then it diverges. Okay? So see, some of these you start learning little tricks like that you can do in your head. Okay? Now, this whole chapter, I mean, most of it is all about these different tests that we're going to do. All right? But what I want to do is kind of summarize what we know so far. Okay? All right. So what we know so far is the two series. Well, we know the geometric series. So the geometric series, if the r that you're multiplying by each time, the common ratio, is between -1 and 1, then the series converges. All right, then we know this p series. All right, so the p series, if the p is less than or equal to 1, it diverges, like the harmonic series. So the harmonic series, the p is equal to 1, it diverges. Okay, then we have the tests. And so as we go through each of the tests, we're going to add to this list of tests. So the first test that we did was the nth term for divergence, where we took the limit as n approaches infinity. Okay, then we did the integral test just in this section. And so the series and the integral either both diverge or converge. So if we can do the integral, and then we'll know. Okay? Now, in the next section, we're going to do comparison tests, but you don't need to write that down yet. Okay? So, let's look at another example. Okay. So, just to kind of get you thinking about it. So, if the kind of the way, the process that you go through when you're, because see, like on the, back in the day, I used to give 100-question final. I don't anymore. But because on the Moodle, it works a little different. But on a 100-question final, I used to give like 10 of these. They'd all be mixed up. And so you'd have to kind of learn a process to go through. So like this one, if I wanted to know, does this diverge or converge? Then what you do is you say, oh, here, 1/2 is raised to the n minus 1. So as n goes up, you're multiplying by another 1/2. So this is a geometric series. And the r is 1/2. So if the r is 1/2, then the series does what?
Converges.
Converges. Okay? So once you start getting into the flow of these, a lot of these you can just look at it and tell. Okay? All right, so this is not a geometric series. Okay? Because you're not multiplying by the same number. This is not a p-series because of the plus 1. Okay? So that means we have to do something else. Okay? Now, so let's say that we want to try the integral test. Okay? Oh, by the way, if we did like the nth term test, see, as n goes to infinity, we'd get a constant over infinity, which is 0. The nth term test doesn't work when you get 0. Okay? All right, so let's do this integral. So the limit as b approaches infinity of 1 over b of 1 over n squared plus 1 dn. All right, now, does anyone remember what this integral is? Either of you remember what this one is?
Would it be the natural log of n squared plus 1?
No, because you don't have the derivative of n squared plus 1. You'd have to have 2n up here. Okay? That's a good thought. Jada, do you have a guess?
No.
Okay, that's all right. This is the inverse tangent. Okay? So this is the inverse tangent of n. So you evaluate that from 1 to b. So it's the inverse tangent of b minus the inverse tangent of 1. Now, so as b approaches infinity, this is the inverse tangent graph. Okay? So you might even remember when we did the inverse tangent graph, I told you that this, of all the inverse trig functions, this was the only one that it would help to memorize because it just pops up in crazy places. This is one of those crazy places. Okay? Because as the x goes to infinity, the y value approaches pi halves. Okay? Now, you could always graph that if you needed to. So this is going to be pi halves. And then you say, well, the inverse tangent of 1 is pi fourths. And so then your answer is pi fourths. Well, that's not really, the answer is that it converges. Okay? We don't really know what it converges to, once again. But the integral went to pi fourths. Here, I'm going to rewrite this. So the integral went to pi fourths. So that means the series converges. Okay? It's a lot of good review in that problem there. Okay? All right. So see if you can do problem 4. All right, so Weston, what do you think?
Why am I thinking that? Okay. Yeah, it converged because we just pull the 5 out.
Yes. Okay, see, you're figuring out the big idea for today is as we learn these, things like the inverse tangent is going to converge. And So if I put a problem on a quiz where I've just thrown a 5 up there, I'm really not trying to make it harder. I'm trying to make it an easy problem for you. Okay? So this is just 5 times a series that converges. So this converges. Okay? So the answer is going to be 5 pi-4ths to the integral, but really it's just 5 times a converging series, so it converges. Okay? All right, so Jada, you good with that one? Okay. All right, so the integral test tells us the series convergence or divergence, but not the sum of the series. So like I said, the series is less than or equal to the integral. So if we know that the integral converges to something, that doesn't mean that the series converges to that necessarily. Okay? All right? Okay, so now let's look at this one. Okay? So let's say I want to know, does this series converge or diverge? All right? Now, you might say, well, let's try the nth term test. Well, see, it's not geometric. It's not geometric. It's not a p-series. The nth term test doesn't really work here because, see, as n gets bigger, then constant over infinity is going to go to 0. So the limit as n approaches infinity of that is going to be 0. So on the nth test term for divergence, when we get 0, then that's nothing. That's not the answer. We got to keep working. Okay? So then let's try our new integral test. So we're going to do the integral from 1 to infinity of n e to the negative n squared dn. Okay? Now, this is a pretty complicated integral. All right? But we know how to do it. It's just going to take us a little bit of work. All right? So we'll start off rewriting as a proper integral the limit as b approaches infinity of the integral of 1 to b e to the n divided by, so the e to the minus n squared, I'm using the elevator rule and bringing it to the bottom. All right, so now I'm going to let u be n squared, and then du is going to be 2n dn. So then, so I need a 2. So if I'm going to have e to the u, du over e to the u. But to get a 2 there, I need to multiply by a 1/2 out front. All right. So this is actually the integral. So now I'm going to use the elevator rule to put that back upstairs. So this is going to be e to the negative u du so the integral of e to the negative u is e to the negative u divided by -1 so that's -1 over e to the u. Seems like I could have done that a little easier. All right, so now I plug in. So I get -1 over e to the b minus -1 over e to the first. So then when I plug in infinity, I'm going to get negative 1 over infinity. So that's going to be 0 minus 1 over e, plus 1 over e. So 1/2 times 1 over e is 1 over 2e. All right, so what does that even mean? What does all that mean?
It converges.
That means that it converges. So all of that work, really, that isn't the answer. The answer is that it converges. So I got a constant. Okay. All right. So try practice 5. All right. So Jada, when you got it.
Would it diverge?
All right. So, how do you explain your logic? I'll tell you, you're right. Or tell me how you came up with that.
Okay, so I just did the integral test, and
Okay.
then I basically just took the answer or the integral of n squared, and it was 1 over n or negative 1 over n.
What is it? What's the integral of n squared?
Negative 1 over n.
No. N squared. When you do the integral, you add 1 to the exponent and then divide by that. So it's going to be n cubed over 3.
Oh.
Okay. All right. And so then you plug in the b, and then you plug in the 1. So you get infinity cubed over 3. That's infinity minus 1/3 is infinity. So therefore, it diverges. What happened to my rest of my word? Okay, so you were right about that. Okay, so Weston, did you do it that way?
I kind of just looked at it and figured it diverged because of the way it's just set up.
Okay, so what was it that you were thinking about there that led you to think that it was diverging?
Just kind of I think talking about the geometric series, but I can't
Okay.
find it in notes.
Okay.
My notes, but
So let's think about this. Is this geometric? Well, I mean, it's just n squared. So we start with 1. So 1 squared is 1, and then 2 squared, and 3 squared, and 4 squared. So we're not multiplying by the same thing each time. So it's not geometric.
okay.
Okay.
But I don't know. I just thought it just keep adding up to infinity.
Okay.
And
So I don't want to put words in your mouth here, but are you thinking of like the nth term test?
I think so.
Look at what is the term doing as n goes to infinity.
Yeah.
Okay, so that's another way to do it. Okay, so if we do it by the nth term test, then you take the limit as n approaches infinity of n squared. And so that's infinity squared, which is infinity, so it diverges. So that is a much easier way to do it. Okay? So if you can do the nth term test, it's easier than the integral test almost always. Okay? Now, the nth term test is for testing for divergence only. And remember, if you get an answer of 0, then it doesn't give you any information. But if the nth term goes to infinity or anything except 0, then the answer is it diverges. So, see, look at the work there versus the work here. Okay? So that's what kind of the moral of this problem is that I want you to understand that as we learn different tests, I'm also going to try to help show you why a certain test will be much easier in a certain situation so that it can save you some work. And so the more of these tests that you practice and get good at, it will really help you. What I'm hoping is that, you know, like when you take the test for this chapter, that there'll actually be, you know, only about half the problems you'll even have to write anything down. Okay? So anyway, so that's kind of what I'm hoping to do in this chapter. So we're still in 10.3. So next we're going to do 10.4. But I think we're good for today. All right? We've only got 10 minutes. And I don't really want to start the next section. Okay? So, but I will be posting probably tomorrow before class. I'll be posting the quiz for 10.3. And I put up all of the guided notes for the whole rest of the chapter. Okay? So those should be available. All right? Any questions or concerns before we call it? All right. Thanks for working hard, you guys. We'll see you tomorrow.
Have a good rest of your day, Mr. Tom.
Thank you. You too.